Thanks, Jim. So I'm going to start a timer. I don't usually do that, but I feel like if I go too over, people will be less happy. So that's loud. Can everybody hear me if I don't have this thing on? No, I have the other one is, yeah. All right, well, I'll keep it over here. Okay. So probably won't get to the dynamic networks part because I might be too long, but we'll see. So the general idea is that we tend to model networks for sort of lots and lots of different reasons. I don't need to sort of go over them, but there's obviously applications, sociology and econ, biology, epidemiology, and the fundamental theory questions on the modeling side are, in my opinion, sort of very much assumption-based. What kind of assumptions do we need to make in order to perform the inferences that we're interested in performing? And depending on how you structure the assumptions, and I'll make that very clear, you can either fit a nicer model, you might be able to perform some kind of counterfactual inference or causal inference, but you also care about what happens when these assumptions fail, how things fall apart. And so the area that I have been focused on a lot in the last couple of years is sort of how do you perform inference, causal inference, in the presence of networks, either through experimental design, where you actually control how treatments are allocated, but the network just plays some kind of role. But similarly, you might be interested in epidemic modeling, which is the dynamic network part that I may or may not get to, and maybe some kind of link prediction, where you try to sort of leverage some underlying structure and sufficient assumptions in order to say, those people are probably going to be connected or should be. Just a little bit of sort of motivating data, and this is sort of a toy example of some kind of interactions between countries, and you might want to run some kind of regression. And the point is the naive regression that's written down here, which sort of sometimes referred to as network regression, could leave you in sort of a very problematic place where you haven't accounted for all of the possible interactions between the countries or any kind of dependence that might be present. So what people frequently do is they'll run some kind of OLS that gives you an estimator for that beta. But what you probably really want to do is something like this GLS, this generalized least squares, where you've incorporated the covariance structure between the entries in your network. And what I'm plotting here is actually residuals. So what I do is you run your favorite OLS, you look at the residual matrix, and then you try to look at the right and left eigenvectors of that matrix. And what happens is that there seems to be a lot of structure in these eigenvectors, right? Europe seems to be up here, Asia is down here, these are the row eigenvectors, the column eigenvectors also seem to have some kind of structure, and if you don't account for this structure, you'll have imprecise inferences, and you might draw wrong conclusions in sort of a network regression setting, and any kind of predictions that you make are going to have the wrong confidence about them as well. One of the reasons you might care about this type of stuff is because eventually you might want to do some kind of causal inference. So this is Facebook. That's a company that people 20 years ago used to use to connect with their friends. And they want to change their ad algorithm. And if they want to change their ad algorithm, that could make them a lot of money, but it could lose them a lot of money. So what are they going to do? They're going to run an experiment. And the thing is, this experiment has to try to give them access to something called the total network effect, right? Because what they really care about is what happens if I treat everybody versus I treat nobody. But you can't really do that by just randomly assigning treatment throughout the network, because you're going to have very weird interactions between people who have a few treated friends, people who have very few treated friends. So trying to understand what is a good design here, maybe in a model-assisted way, is very important. So in really nice work, Johan Ugander and Michael Carrera and company came up with a really nice framework for graph cluster randomization. And they summarize it, I really like this sentence. Essentially, take your graph, if you're interested in this total effect, cluster it in whatever way you want to cluster it, and then randomize at the cluster level. And now if you've clustered correctly for the purposes of what you're trying to learn, you now have access to microcosms of the network. And so this cluster looks like a network. This cluster looks like the full network. Comparing this cluster to this cluster is OK to estimate something like this. And the question now is, how do you actually find these clusters? And they have sort of a lot of theory suggesting that some clustering methods are better than others. And what we're going to try to do is to think, well, we know all of this network modeling from this network modeling literature that there's a lot of structure in networks on top of the type of clusters that they need to use. Maybe we can leverage this network modeling in order to improve this randomization strategy. So the very high level, probably unachievable goal today is to do sort of this overview of high quality network regression. I'm not going to talk about the implementation, but everything that I talk about is implemented in the AMIN package in R. Then how do you actually leverage latent network structure to improve regression outcomes? So we'll see sort of there's some missing pieces that might be happening in the general setting, and so then you want to improve on those. Then you want to try to do that for experimentation. And this last thing is about flexible dynamic modeling for epidemics, which I'm looking at the clock now, and it's not going to happen. All right, so we need sort of the framework. The setup here is you have n actors or nodes or individuals. There's a sociomatrix Y that captures some kind of dyadic relationships between individual I and individual J and the entry Yij. We can leave the diagonal undefined. We can define the diagonal. For my purposes, it doesn't really matter. If it's not defined, all of the modeling toolkit that I have doesn't care. It imputes them and integrates over my uncertainty over it, so I didn't actually gain or lose anything. And if there is meaning to YII, then obviously you're more than welcome to introduce that. And then you might have some kind of covariate structures. They might be node-specific. They might be dyad-specific. And you might want to know how those x's interact with those y's. Are they predictive of them? Are they not predictive of them? So, and I don't know, I don't think, there hasn't been like a social relations model. Has this slide been up before in the last 3 days? No. All right. So this is arguably the first, sort of the simplest social relations model that sort of suggests that my interactions with each person are dependent on these two parameters, AI and BJ, which capture something like sociability and popularity, right? If my A's are big, I make more friends. If my B's are big, I have more friends made to me, right? So imagining this as a directed network. And this is essentially an ANOVA. And so we have a lot of tools in order to run ANOVA. The reason why it's not exactly an ANOVA is because you probably want a little bit of dependence between AI and BI, because my sociability might be similar to my popularity in some sense. And then you might want some excess dependence between epsilon ij and epsilon ji to capture reciprocity and ties and connections. But what's nice, this is sort of a very complete picture for sort of a baseline network model. It captures a lot of behavior. It captures variability in degree really nicely. It's able to sort of accommodate a lot of information, and everything else sort of falls into these reciprocated epsilon ij's. But obviously, this is not enough, and we might want to introduce some kind of covariates. This is what we might be after. We're interested in whether or not smokers have more friends or fewer friends, and so you might introduce this just into a sort of general regression framework. And what's sort of interesting here is that we're able to think about row covariates and column covariates as, again, having some kind of meaning, right? These are covariates that affect sociability or covariates that affect reciprocity. And I'm going to talk about what these dyadic covariates are going to let us do. But what they're going to let us do is try to capture all of this excess stuff that's not captured just by individualized level effects. The reason why we sort of allow for row and column covariates to be different is because some things just might not matter for those. And so the nice thing is that the framework is sufficiently flexible to model everything out. So what's missing, though, and I'm alluding to it throughout, is the ability to capture actual network behavior that we know is present, right? Some notions of stochastic equivalence or homophily are not capturable just by additive effects. And so a natural place where that gets buried in a lot of models is in these dyadic effects. So just sort of to remind us what those two things are, homophily is the fact that I have similar friendships, and stochastic equivalence is that the people I am in the group with, we send relations to others in the same way. Those seem to suggest some kind of higher order effect than just the direct effects of sociability and popularity. So these are triadic behaviors. And a natural way to sort of try to capture homophily is by introducing dyadic covariates that capture the similarity between individuals. So imagine that xi is the fact that I play soccer, and so I am more, if you also play soccer, then our xi xj is going to be equal to 1, and that's going to increase the probability of us having a friend. And by the way, I'm talking about connections here as if they're binary, but in this case, specifically, everything is sort of continuous. Binarizing this is very simple, and I show that in a couple of slides. And so you can do sort of a much more general type of dyadic interaction that can be captured sort of by taking any types of row covariates, any type of column covariates, and interacting them. And there, you can capture sort of these dependencies at whatever order you want. Now, oversaturating these models is not a huge problem just because we have so much data, but you do want to think a little bit carefully about what you are actually introducing into any kind of fitting, because you might be wasting degrees of freedom. And so there could still be excess correlation, though, and the reason we introduced those additive AI and BJ was because we were trying to decompose excess correlation into things we can interpret. And so this dyadic structure that could still lead to excess correlation suggests maybe introducing a multiplicative model. And so imagine that there's some kind of latent behavior, and this is why these are latent space models, because the A's, B's, U's, and V's are latent. Imagine that there's sort of latent homophily or latent structural equivalence that you're trying to capture. And why are these multiplicative effects playing that role? Well, if we think about where they come in, so again, thinking about this as sort of just a continuous thing for now, if my sender behavior is similar to somebody's receiver behavior, it doesn't matter where you are, the U's don't have to be positive because the inner product just needs to be big, then my Y's are going to be big. And so that's going to capture one side of the problem. If my U's are similar to somebody else's U's, then that means I send ties in a similar way to my friend. So I'm able to both capture homophily and stochastic equivalence here very nicely. And this sort of is starting to look much, much too complicated, but what's nice is that we do this in a Bayesian framework, everything gets sort of nice normal priors, and it's fairly easy to fit. I don't actually have all of the math in this slide deck, but if there's interest, I'm happy to sort of pull that up in a little bit. And what's important here is that some of our favorite models are a special case of this class of models. For example, the stochastic block model is exactly in this universe, because you can think about this UI transpose Vj as UI being which class I belong to, Vj is which class somebody else belongs to, and this inner product, and you can maybe stick a lambda in here to say how much being in the same class increases our probability of connecting, how much being in different classes leads to us being able to connect. So for binary data, this is fairly sort of straightforward. You introduce a binary indicator, so the Yij's now are the indicator that this Zij is bigger than 0, and you go on from there. Again, what's nice is that all of the math that's worked out for the continuous case naturally works for this way via this data augmentation machinery. And stop me if there are any questions or if anyone wants me to go into the actual details of how to do this. Yeah?
So I know a couple people in here use classroom data, and you might have like within classroom ties and not between classroom ties. Could you use this to, based on the classroom dynamics and the similarity between, say, U and V, or not, like the propensity to develop a tie between classrooms of like, say, classroom 1U and classroom 2U?
Yeah, that's a really good question. So there's nothing for me to write with. Maybe there is. Yes. The answer is yes, as long as you're willing to make enough assumptions. And so if you think about sort of this is my sociomatrix, what you're saying is that, let's imagine there's only two classes. So I have observations here, and nothing here, and nothing here, right? And so if you're willing to say that all of these kids are in the same school, they're embedded in the same space, again, because we're very easily equipped in order to accommodate missing data, I can easily construct predictive distributions over this stuff, again, under this possibly restrictive assumption that everybody lives in the same latent space. Now, if this is this ninth grade class and this ninth grade class, probably reasonable. If we're talking about ninth graders and 12th graders, maybe slightly less reasonable. However, they will probably share some features, right? So, both ninth graders and 12th graders can belong to the same football team. And that would come through here. So the short answer is yes, you can do that. And as long as you sort of state your assumptions of what's going on, you are more than welcome to do that. We've done, and the canonical example for the data that we work with are these ad health networks. And we've thought a lot about how to sort of deal with both the same-sex and the cross-sex friendships and whether or not it really makes sense for them to be embedded in the same space or not. And so that's sort of in the same spirit of questions. Okay. So nicely gets us to the ad health data. There's a ton of data on sort of different sort of sufficiently small networks that we're able to fit with this in a Bayesian setting. And our goal is to relate network characteristics and individual level behavior because we really care about whether or not we need to intervene on smokers and whether or not we should maybe intervene on their friends so that the smokers stop smoking. So largely there's sort of a huge literature on this, and you've seen lots of ergums. You've now sort of seen this introduction to latent variable models, but some of the commonalities between them is that the assumptions are very, very strong for all of these. In particular, one of the assumptions for both ergums and latent space models is that the data are fully observed, the way that I've framed our thing. And the data in ad health and in Prosper are certainly not fully observed. And they're not fully observed structurally. For some kids, you know how many friends they have in ad health. For some kids, you don't know how many friends they have because they've nominated the maximum allowed number of friends. They might have 7 more friends, or they might not have 7 more friends. Yeah. So, yeah, no. So, that's right. So that's, in baseline ergums and baseline latent variable models, that is the assumption, right?
Well, I mean, by baseline, you mean
Sure. I mean, baseline these ones as well, right?
Yeah, baseline.
Exactly. That's exactly what I'm saying. Yeah. Yeah. Right. So the assumption that you need to do something to the model that I had written down in order to fit ad health data. That's the point. You need. Yeah. Right. So, and then there's sort of this additional assumption that the effects of covariates on network formation are identical across units. And again, sort of thinking about the structure here is that those betas don't vary according to some additional unobserved latent features. And that is fairly restrictive in this setting. So here's some ad health data, and we restrict ourselves to male-male networks because of the way that the data are collected. Those kind of make more sense. the cross-sex networks are, we think that the actual measurement is measuring something different than the same-sex networks. And so you can fit some model. And this is sort of one of the schools. We fit this one model using this framework, and we can find maybe that sport involvement has some kind of increased effect on sort of your popularity, which is maybe not that exciting and not that surprising. Everything else seems to be zeroed out. And one of the reasons that this might be the case is that maybe there's additional structure that's missing because the assumption that everybody has the same interaction from their covariates to network formation is inappropriate. So we can run some community detection algorithm, split our data in two, and then run the same thing. And if we do that, then we can start finding maybe there is some additional structure. So for example, it looks like maybe sport involvement matters for one group, doesn't matter for the other. You have to squint really, really hard in order to get this. But the issue with doing it this way is that you're ignoring the uncertainty in the community detection process. And the whole point of having this fully Bayesian framework is that we're able to actually capture uncertainty about how important any of these covariates are for network formation. So this is joint work with Heather Matthews, who graduated last year, I guess? Yeah, a year ago. On sort of incorporating this excess community structure into these covariates. So essentially what we want is something that allows us to vary these network coefficients according to something. Maybe according to group, maybe according to some other latent structure. Maybe we want them to be continuously varying somehow. And so if we recall, right, these U's and V's connect nicely to the stochastic block model universe. So maybe if we think about the U's and V's as being our as binary covariates, maybe looking like this, where there's an extra matrix in the middle, then we can sort of map between the U's and V's that we're learning and these group identities that we want to give people as they interact with others. So let's think about U as this n by k matrix. So in each row, you have exactly one, so you can belong to only one group. It's fairly simple to make this more general, but that's what we sort of are thinking about. Same with the V's. And essentially, our goal now is to construct these row and column coefficients that are no longer just a beta for how much me being involved in a sport affects my friendship-making ability. It might matter also whether or not I belong to community A or community B. So this is just sort of an illustration of how this works out. And essentially, in order to calculate these quantities, these are just simple linear algebra tricks. The reason the simple linear algebra tricks are interesting and important is because they facilitate computation. Otherwise, it would require us to sort of blow up these matrices, making this nearly impossible to actually run. So this, we called it community-dependent additive and multiplicative effect network models. Start looking like this. But what's nice is that these betas retain the same interpretation, but now they're sort of capturing not the effect of this particular X on network formation, it's this particular X for people in each of the groups that might exist. And these X's groups might be sort of interesting and important to work with. What's also nice is that if there is no group structure, we're not losing much, because in reality, summing up over these betas is just, it nicely relates to the original Amen model. So here's just a simulation to sort of, there's a lot of not pretty notation here, but essentially just 3 community structure. There's 50 nodes in each community to make it easy, and there are some community independent covariates. So the first row and the first column covariate are the same in each community, so you could think about not fitting a community structured thing here and fitting a community structured thing here. Importantly, the U's and V's are not observed, so we have to learn them at the same time. And what we're going to do is we're just going to throw this into this framework, not telling it which is a community structured thing, which is not a community structured thing, and see what comes out. And let's sort of take a look first at the left. Unsurprisingly, if you are fitting the standard model that doesn't think about the fact that there could be differences, in the independent covariates, it's doing fine. And that's because of that identity that we can show for these types of models that it's going to be okay. The problem arises when you start fitting these community-dependent covariates. And I made that so that the first one is -1, middle one is 0, the top community is 1. And so the average of those is 0. And so you're actually going to find that nothing is important in this case, which is not good. On the other hand, if you go to our structure, you're actually going to be okay. So if you kind of wasted energy here, right? Like you learned the same number 3 times. There are ways of sort of avoiding that or shrinking these to be the same number if you've decided there is no community structure here. But here we're able to actually detect the various individual covariates. And these confidence bands that we're seeing there, these are credible intervals that incorporate the uncertainty in actually learning the U's and V's, which is important because if we first learn the U's and V's and then just fit 2 models, or 3 models in this case, we're going to lose all of that, and we might be either overconfident or underconfident depending on which of these 2 problems we're solving. So in that specific school, we went ahead, we did this, and then we wanted to look at the characteristics. This is 2 schools. I think we're seeing the results for this school. We see sort of that these communities don't seem to completely vary on observed characteristics that we can include. So these communities that we're detecting, which I think they're on the order of like 50-50 or a little bit less than 50-50, they're capturing something else. Now, I'm not going to go into and try to sort of overinterpret what they're capturing here. But one of the things that we've been doing in a lot of other work is when we find results like this, we can try to go to other data that is available about the people that we're studying and try to sort of understand whether or not these structures that we're finding are actually meaningful. And so if you do this for this school A, what's nice is that, so in this school, there's no difference between the 2 communities, and we've essentially just wasted some energy. And that's okay, that happens. Whereas for school B, we do see a difference specifically on sport involvement. We see that for one of the communities, there is no effect of school involvement, and for the other community, there appears to be an effect of school involvement on link formation. This story would have been probably much more interesting if these results were, excuse me, much, much stronger for something like smoking, where we do see sort of essentially 0 here, and then something that crosses 0 in the credible interval, but not necessarily. It does look like maybe there's a difference there. And the reason this is important is if I were to go back and try to intervene in this school, maybe I treat these 2 groups differently if my intervention has something to do with smoking. Excuse me. Okay. So why do we do any of this? Well, this is essentially learning what covariates might be important. This is an important link prediction problem. It can sort of get us access to what kind of data we might be interested in collecting in the future. But maybe we want to run an experiment on a network. And so maybe we can learn from the fact that there is a lot of this structure and think about how do we run a better experiment than just graph cluster randomization. So this is our Facebook network. And again, we're interested in capturing, for example, this quantity. And what I'm showing you here is a stylized example of what happens using graph cluster randomization. In this network, you're going to run graph cluster randomization. The first step of it is a clustering algorithm. And I don't remember if this is one hop or whichever algorithm we use, it finds these 3 clusters. But you're now all very highly trained network sleuths, and you can see that these look like some similar people. These look like similar people. There's some very few connections in between them. So maybe this red chunk, they look similar. The blue people look similar to each other. The purple people seem to be pulling from both potentially communities. And the thing is, just like we might believe that link formation changes as a function of which communities you belong to, maybe some kind of outcomes that you can measure also depend on the type of community you belong to. So one of the common assumptions in the causal inference literature is that only my friend's treatment affects me in excess of and plus my treatment. So this is called network interference, and or neighborhood interference. And there's a large literature that suggests that maybe behavior is actually different between different communities. And so why not modify this assumption and say that the treatment only within the treatment of my friends only within my community can affect me, and the treatment of my friends across communities does not affect me. So that means that now there's a lot that this doesn't fit with. For example, product adoption, it's the opposite, right? In product adoption, it's really important if somebody external to me seems to take on a product, but it's realistic in other settings. And so we need a new design, graph cluster randomization. Thanks. So we need a new design because graph cluster randomization does not accommodate that assumption. So what do we do with that? Well, the old design did this. The new design says, let's cluster communities first. Let's get these guys and these guys separate. And then do graph cluster randomization inside each of these communities. So importantly, the clusters in graph cluster randomizations are not meant to be human interpretable or scientist interpretable clusters. They're a tool of the randomization technique. And so, but the thing is, there are also potential communities within which you want to learn these tools. So if you do this, you'll do better, so hopefully. And so here's just a sort of a naive simulation. What we're showing here is relative bias compared to just randomly flipping a coin. So the relative bias in the design. So the first one is called epsilon net. This is the graph cluster randomization that's done naively, does not know about community structure, even though the community structure is important. And you can ignore the variability across this line, but essentially it's performing better than just flipping a coin for each individual, but not by much. What you have here is this community aware where you know the true community structure. And so then you can do much better than randomization, than just coin tosses, about 12% better in terms of bias. What you're seeing in orange here is what happens if you have to do community detection in your first phase. And the x-axis represents how easy or how difficult the community detection problem is. So you can imagine sort of moving this way along it makes the community detection problem more difficult. So when the community detection problem is really easy, we perform almost as well as the Oracle method that knows the true communities. Because when the community detection problem is easy, you actually know that almost any community detection algorithm concentrates on the true communities really, really fast. As the community detection problem gets more difficult, you start doing worse than this. And this is over randomization. So this is incorporating the fact that there is uncertainty in the community detection problem. But what's nice is that you actually never perform worse than ignoring the community structure altogether. To sort of be clear, what this x-axis, you can think about if there's only two communities, the within community and across community probability is getting more and more similar to each other. Okay. So what would you like me to? This is a place where I can stop, or I can show another picture, or two.
Let's stop.
Okay. All right.
I'm not usually in the driver's seat in that degree. Comments for Alex, please. I want to start with a very basic one then. Is this built into the AMN package now?
The experimentation stuff or the model fitting? No, because Peter's, no. One of the plans is to try to get everything sort of have this. The code is available on Heather's GitHub, and it uses the exact same syntax as the Amen package. It just uses a few computational tricks that we didn't want to sort of, but eventually it will be in the Amen package on its own. So I really care about sort of this experimentation problems, and one of the things that is important here is that this is sort of a naive model-assisted design, but you could imagine sort of trying to think about what are the things that could influence an experiment, regressing them out essentially before running the experiment, and then trying to design an experiment that, when I say design, sort of decide who to assign to treatment and who to assign to control in such a way as to get you the best chance of estimating the causal quantity that you want. And so maybe if there, no, go ahead.
Yeah, I had a question, I guess. When there's clustering in a network, it's usually because there's some basis for that clustering. And I guess I'm wondering how, if you're applying interventions to some clusters, not others, that whatever that basis is might moderate the effect of that intervention. Are there other ways to either factor that in, things that might be possibly the source of clustering, or otherwise tell how clusters differ?
So I'm going to answer the easier version of the question first. And that is sort of, this is why this could take 20 to 30 minutes explaining sort of the point of these clusters is not, these clusters are not meaningful. Their sole purpose is to find tight-knit clusterings that look similar throughout the network. If your network looks very, very non-homogeneous, this could be fairly weird. And so the idea here and the way they sort of apply it to a generally more or less homogeneous network. So that's, so when you're, this I guess is using epsilon net, which is essentially saying, take a bunch of seeds, go out from them, define radii around everybody, and put everybody who's within a small radius into the same cluster. And so you're going to find lots and lots and lots of clusters. So one of the questions that frequently comes up is why not use a community detection algorithm here? And essentially it's because community detection algorithms do less well as the number of communities increases, and you want large number of communities for this phase because you want to be able to randomize lots of different clusters into different treatments and controls. And community detection algorithms sort of need there to be a ground truth for them to be meaningful. Otherwise, you don't really know what you're getting. So this is why sort of these random walk type of clustering algorithms or walk type of clustering algorithms make sense in this type of phase. There are other ways of designing experiments on networks that can take into account lots of this stuff. And we have other work which takes a sort of a very a much more optimization-y approach, where it says, hey, I know that the way in which my friends might influence me has this type of structure. Let me find all of the types of randomization, excuse me, all of the types of randomizations that would minimize bias in a hypothetical experiment. That is a very computationally complicated thing to do, but it's doable. And so we have, one of our papers does approximately that. Okay.
Maybe a quick follow-up to that
Yeah.
question. I was involved with a group that had a process much like this, and we were really concerned about making sure our treatment and control groups were separated, and so we did this kind of very, very similar to your top design there. But we really wanted to make sure that there was little overlap between our treatment and control as possible, and that limited the number of, essentially, a number of intervention cases we could do in any given set, and they were small settings, and so it effectively, we lowered our power because we didn't have the ability to pick, a dozen seeds. We had to pick 6 seeds.
Right.
Right. And so, is there a way? Does this new method help us get around that problem at all, or not?
No. What you're describing is essentially an independent set design, and we know that the number of independent sets grows very, very slowly. In even large networks, you're going to end up with very few independent sets. And if you want to isolate individuals, that's bad. This design won't fix that. But if you're willing to postulate that the way in which my friends influence me is linear and additive, or it doesn't have to be linear, let's just imagine it's additive. I have my treatment effect plus whatever interference I get from my friends. Then we have a design that works really well to give you a nearly unbiased estimator that's lower mean squared error for the direct effect, because we balance the design so that treated people and controlled people have very similar patterns of treated and controlled friends. So that one is easy to do. The second you're interested in sort of other estimands, that's where the optimization problem becomes more difficult. But the other thing that I will say is that while I really like randomization-based inference, at the end of the day, you should not be afraid of modeling things at the end. And so if you're willing to model things, you can design experiments sort of for maybe more interesting questions. And so this is sort of a simulation of what what happens depending on different types of intervention policies on the network for an SIR model. And what you can see is that if you have even strict quarantine for all, it's definitely better than no intervention, but there's a ton of variability here. And so even your independent set design for this type of problem would only be able to capture one of these things. And so you probably need to quantify uncertainty in the actual underlying social process in order to get better understanding of what is it that your randomized experiment even did.
Other questions, comments?
So outside of randomizing, does this have any more like practical intervention is concerned?
So,
Like specifically in the public health context?
yeah, so
Can you repeat the question just so we...
the question was sort of what are the practical implications of this other than just in sort of designing randomized experiments. So the second half, which we didn't do, that I didn't go through, is really meant as a sort of it's modeling these network and epidemic processes that evolve over the network. And maybe I'll just show one picture here. Sort of, a lot of the work underlying sort of epidemic modeling, even during COVID, has ignored the fact that one person infects one person. It's not like any one person can infect any other person, right? And so we incorporate this network component. If you observe networks really well, then you can incorporate the network component into the epidemic model, and that helps you sort of infer sort of how personal characteristics, if you believe if you're willing to make enough assumptions about this process, you can understand what personal characteristics might affect infection probabilities. So just sort of very naively, in this data set, which is the X-flu data, where we only have 100 college students, and a bunch of them got infected by the flu 10 years ago in Michigan, turns out that those who were characterized to have optimal hand washing, whatever that means, were less likely to get infected. So at the very least, that's a public health comment. I don't know that we necessarily didn't know that, but this is one way to confirm that in a setting that is sort of a little bit different than the classical randomized experiments for measuring how much hand washing is important in a public health setting. So yes, so modeling here can give you sort of both this exploration option or experimentation downstream option.
Thank you.